Hi. In these notes, we are going to revisit forced oscillation problems using forcing functions which are periodic but which are not purely sinusoidal. And we already experimented with this when we were doing matrix exponentials when we derived the convolution formula for explicit solutions to forced oscillation problems. Okay, so this will be fun. And the warm-up exercise is going to tell you pretty much exactly how we're going to analyze this problem in a nutshell. And it is use particular solutions from chapter 3 and use superposition, in other words, linearity of the operator on the left, to find particular solutions when your forcing function is a linear combination of sinusoidal functions. We'll talk about what the periods of the forcing function have to do with whether we get resonance or not. Okay, so if you want to, give it a try. And here is how it goes. So for part A, well, in part A and B, the homogeneous solutions are just linear combinations of cos t and sine t, because the omega naught squared, which is the coefficient of x of t, is 1. So the omega naught is 1. Okay, with that in mind, let's do part A. So in part A, the right-hand side is a sum of two sinusoidal functions. The period of cosine t is 2 pi. The period of sine of t over 3 is, well, it's the first t, so that t over 3 comes back to 2 pi, so it is 6 pi. And the period of the right-hand side is the least common multiple of the two periods, which is 6 pi. The natural period for the homogeneous solutions is 2 pi. And let's write down a particular solution to see whether or not we get resonance in this problem. And by linearity, aka superposition, we can just write down particular solutions for each piece, and then their sum will be a particular solution for the whole thing. Okay, so if the right-hand side is cosine of omega naught t, that's down here, the particular solution is t over 2 omega naught, which is 2 times 1, which is 2. The coefficient of the cosine t is 1, that's the capital A, so I get a 1, and then times sine of omega naught t, which is sine t. You might even remember this particular solution from chapter 3. So that's the particular solution for forcing with cosine t. If we force with sine of t over 3, then we are using this particular solution, and we get 1 over 1 minus the omega in this case is 1/3. So the omega squared is 1/9 times sine of t over 3. Okay, so let me clean that up. That's t over 2 sine t. Let's see, 1 over 8/9 is 9/8. And so that's a particular solution for the given forcing function, which is a sum of two pieces. And the first one is a linearly growing sinusoidal function. And so this term is causing resonance in the particular solution. And then the general solution will just be this particular solution plus arbitrary linear combinations of cos t and sine t. So we'll still have a linearly growing term and will look roughly linearly growing itself. So here, the period of the forcing function was not equal to the period of the natural frequency, and yet we got resonance. But it wasn't surprising when we looked at how the right-hand side was made up. Okay, now let's do the second example. In the second example, let's see, the period of cosine 2t is 2 pi over 2, which is pi. The period of sine 3t is 2 pi over 3. The period of cosine 6t is 2 pi over 6. And the least common multiple of these three periods is pi. No, it is 2 pi, which is 2t1, which is 3t2, which is 6t3. And so F is 2 pi periodic. Now let's write down a particular solution. You can already see it's not going to have any resonance terms in it. So for cosine 2t on the right-hand side, I go down here, and so I get a 1 over 1 minus 2 squared is 4 times cosine 2t. When I plug that into L, I'll get the cosine 2t. For the next term, I'm going to use this one. So I will get minus 3 over 1 minus 9 sine 3t. And for the last one, I'll go back down to this table entry. I will get 1 over 1 minus 36 times cosine 6t. And each of these, I could leave them that way, but it looks a little neater if I clean up the fractions. this particular solution is just a happy 2 pi periodic function. There's no resonance. It'll look kind of weird when you graph it because you're superposing 3 different angular frequencies, but it's a 2 pi periodic solution, no resonance. Even though the period of the forcing function does equal the natural period. So this, if we're naive about it, contradicts our intuition from chapter 3, where we thought we would get resonance when omega equaled omega naught. In other words, when the period of the forcing function was the natural period, and that we wouldn't get resonance when omega did not equal omega naught. Or, if we were just thinking in period terms, the period of the forcing did not equal the natural period. But this argument illustrates the fallacy of that idea, because the period of the forcing function doesn't necessarily have anything to do, or much to do, with the angular frequencies of the individual forcing sinusoidal functions. All right, so you'll see that this example contains the content of our discussion in the case we don't have any damping. And it's very close to the content in case we do have damping and are studying practical resonance. So, in this video, we're revisiting forced oscillation problems, and we'll go back to the examples from April 3rd when we were using the convolution formula that we found from matrix exponentials. And we're going to use Fourier series to understand precisely whether or not, if we have a periodic forcing function, f of t, whether or not there will be resonance when c equals 0, or practical resonance if c is close to 0. Okay, and so let's do the discussion. We'll break it into damping and no damping. And so let's do the undamped case first. So then your differential equation looks like x double prime plus omega naught squared x equals f. And we'll think of general periodic functions p, which we'll say equals 2L. And then f has its Fourier expansion for 2L periodic functions that we talked about recently, and the Fourier coefficients are computed by these formulas, which correspond to orthogonal projection of f onto the sinusoidal functions. Okay, so here's the story. You look at the Fourier series for the forcing function. If none of the terms in that expansion happen to have the natural angular frequency omega naught, then the particular solutions for the corresponding term will be the ones that don't have resonance terms in them. And when you add up the series of particular solutions, so in this case it's an infinite sum, you won't have resonance. And actually, the infinite sum will converge absolutely, it turns out, to a nice bounded particular solution. So for sure, there will not be resonance if it never happens that one of your omega n's, and your omega n's, if you look up to the formula for the Fourier series, are over n pi over, are always n pi over L. So if none of those are omega naught, then you don't have to do any more work. You know you're just not going to have resonance. However, it's if one of the omega n's does equal omega naught, and in terms of periods, that means the period of the sinusoidal function is a fraction of the 2 pi over omega naught, which is the natural period, then there could be resonance, or maybe there won't be, and it just depends on whether that Fourier series term actually shows up, which it won't if both the AN and the BN are 0. Okay, and that's exactly what was happening in the warm-up exercise. As in the first one, the period of the forcing was 6 pi, but one of the terms had the omega equal to omega naught, and so the corresponding particular solution corresponding to that forcing term was a resonance term. So we got resonance. And in the second example, right, and remember, for 6 pi periodic functions, this is actually a finite Fourier series. So the omega, the sinusoidal terms in a Fourier series have periods which are fractions of 6 pi. And remember, this period was 6 pi, and the cosine 2t term had period 2 pi. So this is actually is the Fourier series for the forcing function, as we talked about when we were talking about uniqueness of Fourier series. So that's exactly what the general theorem says. You can get resonance if one of your Fourier terms has omega equal to omega naught. And similarly, in example B, f of t is its own Fourier series for 2 pi periodic functions. And even though 2 pi is the natural period. None of the terms in that, none of the Fourier terms in that 2 pi periodic forcing function contain omega naught equals 1 terms, and that's why we got no resonance. So let's revisit some of the examples from April 3rd. And let me just briefly remind you how we figured out explicit formulas for the solutions. I'm not going to redo this in any detail. We started with the second order differential equation. It was equivalent to a first order system for x prime. And we wrote that first order system in matrix vector form using the matrix vector analog of integrating factors from chapter 1 and the matrix exponential. We had an explicit formula for the solutions to the first order system depending on the initial vector x naught and on the matrix exponential. And the convolution formula in the second term depended on the forcing function for s between 0 and t, in other words, since the initial condition up to time t, and on the exponential e to the t minus sa, and so t minus s was also between 0 and t. And in order to extract the solution to the original second order differential equation out of that first order system, we just took the first component function from the formula and we came up with this nifty convolution formula for the solution for any forcing function. It didn't even have to be periodic, it could just be any continuous forcing function. Okay, so the second example we did on April 3rd was we were forcing with the 2 pi periodic square wave. And we were thinking of pushing a swing which had natural period 2 pi. And for the first pi seconds, we were pushing it one way, and then just as it wanted to start going the other way, we started pushing it the other way for pi seconds with constant force all the time, just changing the sign of the force. So I used the computer to compute the solution using the convolution formula, and I just had to define the square wave up to time 30 to know what the solution would look like up to time 30, so that's why I was able to use just the square wave values up until 10 pi. And in the convolution formula, remember, that's what we get when the initial displacement and velocity are 0, because then the e to the ta x naught up here is 0, and this part is 0. Okay, and just as we expected, we got resonance. In this graph, the green, almost invisible graph is of the square wave, and the black is of the resonance response. All right, so let's understand that in terms of the Fourier series for the square wave, which we have been studying mucho. And we'll just do what we did in the warm-up exercise, except we'll use infinite superposition of particular solutions, which can be justified, although it would take work. So the square wave is 4 over pi, sum over n odd of 1 over n sine n t. And our particular solution is going to be, well, and let's write out the first few terms to see what happens. The first term is just 1 sine t. The next term is 1/3 sine 3t, then 1/5 sine 5t, and so on. You can already see that the first term is going to cause resonance. And we can even write out the formula for the particular solution. So, okay, if everything is going to have a 4 over pi in it, this is a linear operator, so I can factor that out of the particular solutions as well as the forcing function. So to get 4 over pi sine t, I need 4 over pi, and I am using this formula, minus t, omega naught is 1, and it's going to be 1 in all of our examples today. And as we were talking about rescaling Fourier series to consider 2L periodic functions last time, this is really no loss in generality because you're just changing units. So that's not practical to do if you have a specific physical problem, but theoretically it totally makes sense to simplify the math. Okay, so we get 4 over pi times minus t over 2 omega naught is 2. The a, well, it was 4 over pi, but we factored it out. So now we're just left with cosine t. The next particular solution, I've got the 4 over pi already factored out, and I've got 1/3, and I'm using this one now. The a was 1/3, and then I have 1 over 1 minus 9 sine 3t. And I keep using the non-resonant particular solution, so 1/5, 1 over 1 minus 25 sine 5t, and so on. And let me isolate the resonance causing term. So xp of t is minus 2 over pi t cosine of t. And I'll just write the rest of it as a sum. So 4 over pi times the sum over n odd, n greater than or equal to 3, 1 over n, 1 over 1 minus n squared sine n t. Okay, so this first term is the resonance term that we saw in the solution, And the rest of this stuff is small in absolute value. So this entire sum, first of all, it's going to converge because it goes like 1 over n cubed in absolute value. So it's convergent absolutely to something small. So the absolute value of the whole sum is less than or equal to 4 over pi. The sum of n odd, n greater than or equal to 3, roughly speaking, 1 over n cubed. That's not quite right, but that's roughly speaking. And you can estimate that sum. It's small, and you don't even have to throw out the even terms, right? The sum starts with a 1 over 27, the next one is a 1 over 125, and so on. Okay, so to emphasize that we've understood the resonance completely in the original picture, we can throw out the original term that was causing resonance, which was the 4 over pi sine t. So the resonance causing term was the 4 over pi sine t. And so we put that in by subtracting it from the forcing function, and then you've got the t minus taus because of this convolution integral form. And when we do that, we get back a nice 2 pi periodic function, which is small, right? It's varying between a little less than negative 0.3 and up to 0.3. And actually, what we're seeing there, remember the particular solution, this is the convolution integral, so it satisfied x of 0 equals 0, x prime of 0 equals 0. The particular solution did not, that we got by Fourier series, did not satisfy x of 0 equals 0. It did satisfy that because it was made out of sinusoidal functions, but it did not satisfy x prime of 0 equals 0. So this was the one that failed. And so to compare our particular solution with the convolution integral, we would have had to subtract off a multiple of sine of t, which is a homogeneous solution, because we already had x of 0 equals 0, and so we couldn't add any cosine t's without destroying that. And so if you subtract off a multiple of sine of t, and I thought about the multiple, and I thought I could tie this into our magic formulas, but I think that's not right. So this multiple is actually not quite right. You could figure out what it is. If you're looking for fun things to do and your first 50 ideas fall through, you could figure out the right multiple, which is not this. At least I don't think it is. Maybe I saw something before when I was writing the notes. But anyway, if I subtract that multiple, I get a really tiny oscillation of what's left. It's only going between minus 0.08 and 0.08. All right, so all of this was to convince you, as if you needed any convincing, that we completely understood the resonance that the square wave caused because we understood the first term in the Fourier series, which had omega equals omega naught. Okay, this was my second favorite example on April 3rd. The omega naught is 1, but this square wave is the period 2 square wave. And the swing wants to swing with a period of 2 pi. The number 2 is not any rational multiple of 2 pi, and so pretty much random havoc is going to occur. And when we started the swing at rest and pushed it, we got this poor kid picture where he or she is just getting pushed back and forth randomly and not attaining any great amplitude and getting very frustrated. And if we tried to understand this using Fourier series, well, we know the square wave of tau which we just used in the previous example had Fourier series 4 over pi sum over the odd integers of 1 over n sine tau. We talked about rescaling Fourier series yesterday in the last lecture, and if we want the period 2 square wave, so as t goes from -1 to 1, pi t will go from minus pi to pi. And so we can get the Fourier series for the period 2 square wave by just taking square of pi t and plugging that in to the square of tau formula. And I forgot my n here. So I just plug in pi t in the place of the taus, and I get the formula for the period 2 square wave. And so if I want to solve x double prime plus x equals 4 over pi, the sum n odd 1 over n sine n pi t. My n pi is never going to equal 1. So I never have to use the omega equals omega naught. I get everything from the non-resonance particular solutions. So I will get 4 over pi, the sum over n odd, 1 over n, and then I'm using the starred formula. I already took care of the amplitude. 1 over 1 is omega naught squared minus n squared sine of n pi t. And that converges absolutely like 1 over n cubed. And, I better get it right. The angular frequency was n pi. So this is 1 minus n pi squared. Sorry, let me clean it up. Okay, so I can do comparison tests to this. These look like, in the limit comparison test, they look like n cubed pi squared. So the first one, when n equals 1, it's just like 1/9. And then I've also got that 4 over pi, that's a little bigger than 1. So the first term is like 1/9, or maybe 1/6, who knows. But then the next term is like 1/27, like, I don't know, like 1/200th or something. Anyway, this series converges to something, with small absolute value. For all t, because the sine term is always has absolute value less than or equal to 1. And that's exactly what the picture showed. Okay, our last example is going to be practical resonance in the sense, not the precise sense that we talked about in chapter 3, but the imprecise sense that a small amplitude forcing function can create a large amplitude response. So here the damping coefficient is small. It's 0.2. The omega naught is still 1. And we'll just go ahead and force it with the square wave and see whether we get resonance. And I'll just pirate these formulas from the techniques of chapter 3. So now we're doing x double prime plus 0.2 x prime plus x equals 4 over pi sum over n odd 1 over n sine n t. And I will just add up particular solutions. And since the omega naught is 1, our first omega in the sum is also 1. So that will end up, and that first sine of t term will end up giving us a large amplitude response. So let's, first of all, remember x is xp plus xh. Because there is damping, the xh goes to 0 as t goes to infinity, and our xp, we also called it the steady periodic solution. And here it is. So let's isolate out the term, the n equals 1 term, which is 4 over pi sine t. And then we have the sum over n odd n greater than or equal to 3, 1 over 4 over pi times 1 over n sine n t. Okay, so looking at the first term here and using our particular solution, we will get the 4 over pi, that's the A, and then 1 over the square root of omega naught, of a quantity omega naught squared, which is 1, minus the omega is 1, plus c was 0.2, so c squared is 0.04. Omega was 1, so the omega squared is 1, and I will get sine of t minus alpha 1, I'll say, because it's the particular solution for the first forcing function. And then we will get the other ones, 4 over pi, the sum over n odd, n greater than or equal to 3, 1 over n. Now the rest of the amplitude of the steady periodic is 1 over the square root of 1 minus n squared plus 0.04 n squared sine t minus alpha n. And the alphas are given by our ABC triangles. I won't compute them. I don't really care about them in this example. All right, so this first term is the practical resonance term, because the omega actually equaled omega naught, but it would have worked also if the omega was close to omega naught, because then that stuff under the square root would still be close to 0. So let's see how big that term is for us. It's the 4 over pi. The denominator is just the square root of 0.04, which is 0.2. So that's like 20 over pi, which is like 5 or 6. So that's what we would call a big amplitude relative to the data of the problem. So compared to the forcing. And the rest of the terms add up to something small. Again, the coefficients of the sine of t minus alpha n look like 1 over n cubed terms when you look at it. So it adds up too small. Okay, so because the forcing function in this problem had some omega n equal to or close to the omega naught, we saw practical resonance. And you can see from how we did this that if that wasn't true, then our solution would have been small and we wouldn't have had practical resonance. Okay, so the upshot of the discussion today is that by using infinite superposition, infinite convergent superposition, we can precisely understand resonance for arbitrary piecewise continuous periodic forcing functions. And we can also understand practical resonance. And the way we understood it in the two cases was we would get resonance if some omega n equaled omega naught. And we might get practical resonance if some omega n is close to. We would get it if omega n is close enough to omega naught and if c is close enough to 0. Okay.